All right. Good afternoon, class. Hopefully you had a nice weekend and also your first week of the semester went pretty well. So anyway, for today, we're just going to continue from last week's lecture, which was these recurrence type problems. So let's go ahead and go into that. And of course, before I move on, I updated the assignment 1 to be due on Friday. So if in case you want to ask any questions during office hours on Friday about anything, you still have the option. Also, my grader has been set for the class. You also can ask the grader as well. And also, there's not going to be a 24-hour cutoff or late submission. So it's due Friday midnight. If it's after that, it's going to be considered late. So it's going to be a 0 then. So make sure you submit it before then. But there's no reason to not have it done by then because really it's just a written assignment, so it's not really too insane. But try to, of course, scan it into a PDF and upload that to the Canvas page. Let's go ahead and start the screen share. All right. So I'll just go ahead and kind of recap these kind of quickly here. So basically, a recurrence relation was just a way to sort of model sort of a runtime of an algorithm. So in 302, you look at pseudocode and try to get the runtime and count number of steps for each part of the pseudocode. Whereas here, it's the same idea, but it's more of an advanced version of just being able to model the runtime of an algorithm. So this one right here, this first recurrence relation, is definitely binary search because you divide the problem in half each time, and each amount of work takes one step. So you check the middle element if it's equal or less than or greater than, and then you jump to one side of the list. So this is basically your typical binary search. And to solve this, we just have to expand this recurrence a couple of times. So typically 3 levels of expansion is good enough. So I guess, the best comes in threes, I guess, or so I guess 3 is the magic number. So we see here, our 3 expansions, we see a pattern that we have 2 to the power 3 in the denominator part of the recurrence, and we have 3 additions at the end. So that's good enough to see a pattern that after I expansions, we have n over 2 to the power I, plus we're adding 1 I number of times. So you want to pick an n value that's large enough that's going to, after we do I number of expansions, this is going to hit the base case. So n being 2 up to the power I is going to reach the base case there, and I is logged to events, so we plug these in. So get t of 1 is just 1 plus, we're adding 1 log a number of times, theta log n. And then this one I'll just sort of skip over. But on question 3, this one was our standard merge sort algorithm. So remember, we break the list into 2 pieces, both of size n over 2. And at theta n is your merge part. So most of our divide and conquer algorithms will use these recurrence relations. So this recurrence part is where we're doing our recursive function calls, and then this part right there, so I'll circle this in. So this portion right here is your conquer part. This is your divide part, divide and conquer. So here, if you expand this recurrence 3 times, we see a pattern, we get this result, and then we sort of collapse these together to get this, which you can definitely see here. We're really going to have 2 to the power I plus I times n. We substitute n to be a value that will force the base case to happen here. So get n plus log 2n times n, theta n log n. So let's do, I think I have only one more I have to really cover, at least for expansion methods, and we'll do other methods of solving recurrence relations. So let's look at the fourth sort of recurrence relation. So I'm going to have t of n equals 2t n over 4 plus theta n squared. And of course, as always, our base case, t of 1 will just be 1. So size 1 input takes 1 step typically. Okay, so let's go ahead and expand this. So we're going to have t of n equals, so I'll just rewrite this over here. And I'll just make this as n squared. So since it's theta n squared, we can pick any function, why not just pick n squared? It's the simplest version of any quadratic function, so why make this complicated? Just pick n squared. Okay, so we have to expand on this. So I'm going to, of course, we have to expand this. So I'm going to plug in n over 4 in for n. So we're going to get t of n equals 2 t of n over 16 plus n over 4 squared plus n squared. So that's our first, actually there's supposed to be a 2 right there, my mistake. So 2 right there. So that's our first step. So let's go ahead and expand this once more. So you want to expand this portion because you want to keep on just finding more patterns. So let's go ahead and expand on this again and see if we can conclude something. So we're going to have t of n equals 2 times 2, and then 2 again, t n over 64 plus n over 16 squared. That's going to be the result right there, plus n over 4 squared. I'm going to try to fit this here if I can. I think I can fit this, plus n squared. If we expand this out, that's going to be the result. So let's go ahead and try to collapse this, because this is a little bit not so, we can definitely see a pattern here, but let's go ahead and just, collapse these. So let's go ahead and do that. So I have to, of course, as always, distribute this 2 to these two terms. So we're going to get 2 squared t n over 64 plus 2 times n over 16 squared. So we have another 2 over here. Actually, no, it's going to be one umbrella. So it's n over 4 squared, like that, plus n squared. So we have this scenario. So now we have to, again, distribute this 2 to all of these terms. So you end up getting, I'm going to sort of shift this a little bit here. So you get 2 to the power 3 over t n over, I was going to go ahead and just sort of just make this simple. It's 4 to the power 3 plus 2 squared n over 16 squared plus 2 n over 4 squared plus n squared. That's our final product. So we can go ahead and sort of collapse this. So we see here that we're going to essentially have the following. So we have, so t of n equal 2 to the power I, because we do I expansions, t of n over 4 to the power I, plus, well, we can sort of rewrite this a bit to have, it'll be really 2 squared, so it'll be 2 squared n squared over 16 squared. This will be 2 n over 4 squared plus 2 to the power 0 n squared over, it's going to be like this. It's going to be 4. Actually, hold on, maybe double check this really fast. Hold on. So this, when you collapse these together, it's sort of expanding in that type of way. So we're going to have actually, my notes over here. So we're going to actually end up with 2 to the power I n squared over 4 to the power 2i, like this, is the result we're going to get essentially. the math. So I think I made a mistake in my notes here. So this is going to be the result. And we're going to do a summation of x equals 0 to I minus 1. So yeah, I fixed my notes then. So that's sort of what this is going to be. So we have always 4 to the power. So you have always 4, 4 squared, and so forth like that. So anyway, this is going to be the pattern. So we have to go ahead and try to figure this out. So once again, we're going to basically, we're just going to, again, set n equal 4 to the power I. Therefore, I equals log 2 of n. Now, before I move on over here, what I could actually do is I could sort of rewrite this a little bit as well by just sort of taking this term and rewriting this as 16 to the power I. So I can actually do that. So I believe you can do that in algebra. So I actually did sort of work this. So I did an example on this. So you can do that, in fact. So now we substitute this stuff back in. Well, we're going to do the following. So I'll try to scroll this down here. Log 4. My mistake. Log 4 of n. So now we're going to go ahead and substitute basically this value in. So we got 2 to the power I. Two up to the power log base 4 of n. And that's going to be times it by 1. Plus this summation from x equals 0 to I minus 1, which will be just sort of 2 over 16 to the power I. We actually can reduce this to just 1 over 8, but I'll just keep like this for right now. And then n squared, we can sort of put the n squared outside of the summation like this. So right now, 2 up to the log 4 of n, we can sort of convert the bases to make this log 2 of n. So we can just say 2 up to log 2 of n over log 2 of 4. So 2 up to the log 2 of n is going to be n, and then it's going to be over, so it's going to be essentially log 2 of n over 2. So it's going to give us square root of n, and then plus this portion right here. So this series is going to, this actually is going to converge to a value, because since we have this, the base of this exponent is less than 1, it will not diverge to infinity. So the formula for this actually is going to be 1 over 1 minus 2 over 16 is how we can solve this. So basically, if the summation goes to infinity, we get this result. So we could have, of course, substitute I to be log 4 of n, but it will make this entire result very sort of ugly. So we're going to just sort of say, for now, we'll assume that I gets very large, or close to infinity. It will go to infinity, and it's going to converge this result, which means that this summation can never be larger than that result. So we're going to get 1 over 14 over 16. So 16 over 14 is the result. So we end up getting square root of n plus 16 over 14 n squared, which will give us a total theta n squared as our result. So for these summations, it's always very nice if they sort of they converge to a value. Otherwise, these become very hard to figure out, because you can get a partial sum you can compute, but then it becomes a lot of 2 up to the power of random logs, and it's very hard to algebraically kind of solve them. So for that reason, we want to make sure that, I mean, I guess for the homework and for the exams, we're going to make it where these will all sort of converge to a result. So whatever I is, no matter how big I gets, it can never be bigger than this value 16 over 14. So we're going to have that multiplied to this n squared, theta n squared, just like that. So I would imagine for the exam and for the homework, these summations, either they become very simple to work out, or there'll be some series that will converge to a value. So that way you don't have to do any really weird substitutions and weird algebra to sort of solve these. So that's the last sort of question on these expansion methods. So I'm going to go ahead now and I guess any questions on anything right now? So I guess you could be asking now or maybe not, but I'll just go ahead and keep talking. We're going to go over the binary, or sorry, not binary, the tree method of solving these recurrences. So one method was using this expansion, which is pretty good, but there are moments where being able to do this tree method is a bit nicer. So for a tree method, all we're going to do, so for a tree method, so for the tree method, what's going to happen is we're going to expand sort of our not base case, but our conquer part. So we're going to sort of, expand, I guess, the conquer portion of the recurrence relation. You want to sort of sum or get the sum. So I guess compute the sum at every level and then determine the amount of levels needed. And if you do that, then we solve the recurrence. So it can be a little bit easier to actually work this out than using the expansion method. So really for recurrences, either one works, but there are certain recurrences where the tree method is definitely the better idea than trying to do it the expansion way, because then you get a very complicated looking formula. It becomes hard, it's easy to make a mistake on certain instances. But let's go ahead and just first cover a simple example. So it's something we've seen before already, but let's go ahead and do this one using a tree method. So I'll have 2 times t of n over 2 plus theta n. So this one is your standard merge sort, so we know it's going to be n log n. Let's see if this method does, prevail on this recurrence relation. So we first start with n, because that's our first one. There's theta of n. And of course, we're going to pick n because why choose something different? That would make the problem more complicated, and the constants don't play a role, so why make this more complicated? So if we expand this, we're going to create 2 recurrences where each one will have n over 2 in size. So we're going to have n over 2, n over 2. So at the first level, obviously, it's going to be n, will be your size. The second level, well, n over 2 plus n over 2 also gives you n. Let's do one more expansion. So we're going to have n over 4, n over 4, n over 4, and n over 4, like that. And if we add these up, it'll also give us n. So we can see a very nice pattern. Every level, we're going to have n as our sum. And then we want to go ahead and figure out, well, what's the height of this tree going to be? Well, I mean, we start from n and we divide it by 2, divide it by 2, divide it by 2. So that sort of operation is the definition of logs. So it's going to have a height of log of n. So I guess I'll write this over here. The tree height is log 2 of n. So I have to add n log 2n number of times. So I'll put the summation here just for the heck of it. So x equals 1 to log 2 of n. N, definitely going to be n times log 2 of n, which will be theta n log n. I mean, that seemed a lot more nicer and easier to do than the expansion method because, well, you can kind of see it kind of expanding in front of your eyes like this, and you just have to find the sum at each level and how many levels you're going to have, and that's basically it. So Obviously, for this problem, you could have worked this out using the expansion method just as easily, but this might have been a little bit easier. Now, we'll go over one example right here where actually doing this tree method is going to definitely be a better idea than trying to do this with the expansion method. So let's go ahead and work this one out next. This will be, I think, number 6 on our list. So we have t of n equals 3t n over 4 plus theta n squared. And then we have t of 1 equals 1. Okay, so in this situation, we're going to break this into 3 pieces, and each piece will have n over 4 in size. And each, we're going to take n squared time to combine, or sort of, I guess, conquer or combine the components together. So we start with n squared. That's our first, element in this procedure. And then we're going to break this into 3 pieces. So n over 4, so I'll put a little lower so it kind of separates nicely. N over 4 squared, n over 4 squared, and n over 4 squared. So we call it 3 times. Each one will be n over 4 in size, and then we're going to take n squared time to attack each piece. Now, obviously, at this very top level, it's going to be n squared will be the sum, obviously, at the root level. And then let's go ahead and work this one out. Well, the next level right here is going to be simply 3n squared over 4 squared is going to be, if we add these 3 components up. So 3n squared over 4 squared is going to be the result of this. And then, okay, let's go ahead and try to, break this down even further. So we're going to have each of these sort of nodes in this tree. We're going to break into 3 components once again. So we're going to have n over 16 squared, n over 16 squared, n over 16 squared. Now I'll just sort of do the same thing. I don't want to write the whole thing out. It would be too conglomerated picture, but it's going to be the same, essentially. So if we add all these up, we're going to actually get the result of 3 squared n squared over 16 squared at this level, if we add these up, because we're going to have actually 9 of these, so we have 9 times n squared over 16 squared. So I just put in terms of 3 squared just to make it easier to sort of see what's going on. So basically, I mean, after we can do one more level, but we can kind of see a pattern that we're constantly increasing this level counter by squared, and then we're taking 4 squared, and then we're squaring that, so we're taking 4 to the 0 power, then 4 to the first power, 4 second, and third, and we're going to square that. So we see here the sum at each level is the following. We're going to have 3 to the power I n squared over 4 to the power I squared, or 4 up to the 2i. We can rewrite it like in this type of form, just like this. So we can rewrite this to make it 3 to the power I n squared over 16 to the power I, which this is sort of a trick you can use. You can sort of, make this a little simpler. So really, it's 16 to the power I n squared is a sum at each level. So do a little bit of algebra there. And also, I mean, my algebra is a little rusty from when I was like in junior high or high school, but yeah. So anyway, this is sort of where we can kind of modify this a little bit to make it into a form that is definitely easy to work out. So in this situation, the amount of levels, well, we keep dividing it by 4, divided by 4, divided by 4. So we're going to have log 4 levels, basically, because it'll take that many times until finally we hit that base case So it'll be log 4 number of levels. I know there's 3 branches, but the highest will be log 4 because we have to, once we keep dividing by 4 every single time, and at some point we'll hit that base case. So then once we hit that base case, we're not going to expand any further. So it's going to be log 4 will be the highest of this. So actually it doesn't really matter if it's log 3 or log 4 because all the logs are off by the same constant factors, so it will not make a difference anyway, but it will be log 4. So what's going to happen is you have to sum this all up now. So then the total number of recurrence, the total number of this total amount will be this. We have x equals 0 up to log 4 of n, and we're going to have 3 over 16 to the power I n squared. And of course, this n squared does not really, oops, going to be x over here. So n squared does not really have any, so this x counter doesn't really apply on n squared. So you can take the n squared and sort of remove it or put it in front of the summation. X equals 0, log 4 of n, 3 over 16 to the power x. And once again, since the base of this exponent is actually less than 1, this is going to converge to a value. So the formula really to solve these type of summations is really just, so whatever this c is, so let's say we have a summation of x equals 0 to infinity, c to the power x, where c is less than 1, it's going to be 1 over 1 minus c is the result. So in this case, c will be 3 over 16. So we can go ahead and just say, well, 1 minus 1 over 3 over 16 will give us 1 over 13 over 16, which will give us 16 over 13. So we're having this not go to infinity, but to log 4 of n, but this series, or this summation, no matter how big this is going to get, there's no way this can ever get larger than 13 over 16. It'll never get bigger than that. So we can set this to infinity and assume that, well, we can sort of plug that number in because we know that it can never get bigger than 16 over 13. So we're going to have essentially n squared multiplied by 16 over 13. That's a constant in front of the n squared, so we know it's going to be theta n squared. So that's how we solve that one. So the only hard part really for these ones is finding the sum at every level. And the height of the tree will be somewhat logarithmic in some way, shape, or form. And really, solving the summation is pretty simple, especially if it converges to a value. The hard part, if it doesn't converge to a value, you can use partial sums. So there is I can probably post the Steve Seiden's cheat sheet, which has all of the summations, all the known summations that have the partial sums for them. You also can look up on Wolfram Alpha, but I could post Steve Seiden's cheat sheet as well onto our class notes. So that way you have that to help you work out some of these summations. But anyway, that's how we solve this one. So it's n squared. So any questions on that? All right, so now let's go ahead and do another example of doing this tree method. So I don't want to go over too many because I kind of want to leave some, for the imagination, or as in leave some for the homework assignment I'm going to assign most likely on our Thursday's class. I'll have a homework assigned, which will be basically working out these relations, or recurrence relations, pretty much. So no real surprise, just maybe some of them can be a little bit more challenging than others to work out. But let's do one last example. So it's going to be number 7, I believe. So t of n equals the following. T of n over 3 plus T of 2n over 3 plus theta n. T of 1, of course, will equal 1. So this one for sure is going to be really a tough one to work out if you do this expansion method, because you're going to have these two different function calls at different sizes. So the one above, I mean, this was also kind of was easier to do as in the tree method, and the one above this, well, we could have done this expansion-wise, but this is one where we definitely want to do the tree method because we have two different sort of function calls of different sizes. So doing this expansion would be really, it's very simple to make a mistake when trying to do that expansion method. And this example is really modeling quicksort when we don't break the list evenly. So remember, quicksort, if you pick a pivot, that's the median, it's going to break it in half and it will be exactly the same as merge sort. This is a case where you picked a pivot where it broke the list into one piece of size n over 3, other one of size 2n over 3. So what's going to be the runtime of this? Well, let's go ahead and use our tree method to figure this out. So as always, we start from n. That's going to be our root of this node. And now we're going to basically break this into two pieces. So we're going to have n over 3 and 2n over 3. So obviously at this level, the very top level, it's going to just be n in this case, because, well, we have one node there. And next level below, well, it'll be 2 over 3 plus 2n over 3. Ends up being n as well. That's interesting. Okay, well, maybe is this a pattern developing, or maybe it's not. Let's take a look. So we're going to expand this into two pieces. So tn over 3 squared, 2n over 3 squared, 2n over 3 squared, and 2 squared n over 3 squared. So in this situation, well, we see the following. So we have 9 will be our denominator. So we can add these up. So n plus 2n. So we're going to end up getting 3n plus 5n plus 4n. So we get 9n over 9 is going to be the result if we add these up. So, we get n again. Let's see. Maybe let's do one more expansion just to kind of, just to sort of see what happens. But I think we can see a pattern developing already, which is nice. But let's go ahead and do one more. 3 cubed over 2n over 3 cubed. This will be 2n over 3 cubed. Then we have 2 squared n over 3 cubed. Then we have 2n over 3 cubed. 2 squared n over 3 cubed. Then we have 2 squared n over 3 cubed. Then we have 2 cubed n over 3 cubed. So I already did the math earlier on this, but this in fact is going to give us 27 over 27 n. So it's going to give us n once more. So we definitely see a pattern emerging. Every level, we're going to get an n in this case. This is actually a very nice example. So possibly doing this with the expansion method, it would have been not so simple to get a nice conclusive answer like this. So this tree method really made it very easy for us to find this pattern. So we get n every single level. So each level, so the sum at each level is going to be, is this n? And how many levels are we going to have in this case? Well, here we have n over 3, and here we have 2n over 3. So n over 3 is going to hit the base case sooner than 2n over 3. So that means this branch that sort of goes the right direction is going to go a little bit further, actually, because this will take more steps to hit that base case than doing n over 3. So in this case, instead of having log 3, it's going to be log 3/2 of n is the number of steps it will take until we finally hit 1 or 0. So we're going to have the amount of levels will be log 3/2 of n. So basically here in our summation, our result will be we're going to sum from x equals 0 up to log 3/2 n of n to give us log 3/2 n times log n. And we know that the base of the log does not play a role for asymptotic complexity. So really this is going to, we can use L'Hopital's rule to show this, but we'll just kind of leave that out. This will be just n log n. So even if we don't break the list in half perfectly, it's still going to be n log n. It might be a little bit worse because log 3/2 is going to take sort of more time to finally hit the base case than always log 2. But the idea is that it will still be asymptotically n log n. Just it'll be a constant factor a little bit worse, which is a constant factor is not going to be big enough to make an impact on this. So it still will be n log n. Just not perfectly n log n, but n log n times some constant is the idea. So that's another example of the tree method. So really it's all about finding the sum at every level, knowing how many levels you're going to have. Typically number of levels will be some logarithm. It doesn't really matter what the base really is, but I guess, you know, it's always good to try to get a more exact, precise result. And of course, once you have this result over here, then it's sort of nice to just sort of then just say theta and log n. So I would say try to use precise values along the way. And at the very end, you can just go ahead and just conclude that, well, log 3/2 n, the same thing is similar to log 2 of n. So, or any base at log for that matter. So theta and log n. Okay. So those were like the basic sort of mechanisms of working these recurrences out. So we went over the expansion method, and we went over the tree method. And really for the homework, there'll be different questions, but it gets really, it's as hard as it is. This is as hard as it gets really with these problems. So it's, I don't really see anything too crazy. The only hard part might be just trying to find the pattern and find the sum at every single level might be a little bit challenging. But other than that, though, it's going to be roughly around this degree of difficulty. So we're also going to do other ones as well. Let's go ahead and first talk about this other method. So I'm going to do one really last hard one. So at the end, I'll probably do one that's going to be really complicated. And also, I'm a little fuzzy on this as well, but I remember I was Dr. Larmore's TA and he kind of went over those ones, but we'll do that towards the end. But for now, let's go over kind of another simple type problem. So the following. Let's do this one. Of course, t of 1 equals 1. So this is a recurrence relation for selection sort, bubble sort, and also for quick sort if the pivot chosen is a very bad pivot. That's sort of the recurrence for that. So it's not really, this could be also applied for not just divide and conquer problems, but it's also selection sorts kind of recurrence relation. So now there's one kind of way of working this out is that, well, we're going to keep on subtracting 1 from n, and we do this n number of times, and then we're going to add theta n number of times to get theta n squared. That method is going to work. But this method was, I was taught this method many years ago, that this is sort of the antiderivative method. So what we can do right now is the following. So t of n equals t of n minus 1 plus n. So I'm just going to use n because for theta n, just pick the simplest version of that function. So what I could do is I can rewrite this a little bit. So minusing it by 1, so 1 is much smaller than n, so that's going to be like 1 will be your delta n in this case. So this sets up sort of the derivative of t of n. So this is like the derivative sort of from calculus, how we do derivatives. We sort of have the t of n minus some small value. So it's going to be, how should we say, exponentially or very close to each other, the 2 points. So 1 is going to be some type of value much smaller than n, so it's like the derivative setup, which implies that t prime of n equals n. So we have to do an antiderivative of n to get t of n. So antiderivative will be t of n will just be, I think it's n squared over 2 plus some constant is antiderivative of this. So that constant doesn't really make any difference because remember for asymptotic analysis, that constant plays no role. Neither does the dividing it by 2, which means that it's theta of n squared. So that's kind of a nice trick, which definitely will be a nice trick for his next problem. But that's basically how we work these ones out. So if you subtract by some value, then this is going to be that antiderivative sort of mechanism to solve the recurrence. Let's go over another one. So I think I have maybe at least one more from this method. Yes, I have one more. Okay, so let's go ahead and do this. Then I do have 2 other recurrents I can sort of go over as well. Those ones are going to be really strange, but we'll get to that in a second. So let's look at a question. Let's look at the 9th recurrence. So we have t of n equals t n minus, and I'll use natural log, so log n, plus theta, theta log n. So this one is a little bit of a interesting one. Not as simple, maybe it is simple to kind of visualize this. The previous one was very simple because it was just subtracting by 1, so we did it n number of times. So that was actually really simple, I believe. But let's go ahead and work this one out the same way we did with the other one. So we're going to say t of n equals t n minus natural log n plus, I'll pick the natural log just because. So now we want to go ahead and set this up into that sort of derivative form, which means you can go ahead and just say t of n minus t n minus natural log of n. And we're going to divide this by natural log of n because natural log of n will be our delta n basically because natural log is much smaller than n. It's asymptotically smaller, so that's going to be our delta n basically. So we get this will equal 1 because we have to divide it to both sides. So I'll just do it like this. Natural log of n divided by natural log of n, which would just be 1. So that means for this example, t prime of n is going to be 1. Therefore, we have to take the antiderivative of this, which is simple. T of n will be n over 2 plus some constant, which we can easily show. It's theta of n. So this problem looked kind of bizarre, was relatively easy to work out if we use that antiderivative method. Just like that. So those were the more kind of basic, how should I say, simple recurrences to work out. So any questions on any of these? I'll just zoom out so you can see the entire thing here. Okay. So I'm going to, I guess since my notes is in this order, I'm going to cover these next 2 problems. Now these ones are really bizarre. This one involves substituting and renaming variables to kind of make this, to put it into a form that's going to work. So I'm a little bit like not an expert on this one, but I kind of can solve these. But let's go ahead and talk about these next 2 problems, which will be sort of difficult. It's in the MIT book, these 2 problems as well. But it doesn't explain this perfectly in the MIT book either. So I kind of had to sort of, use vigorous hand waving to sort of show this one. But this one is going to be the really tough one. Or not so tough, but it's definitely a strange one. Theta of n, theta of 1, sorry. And of course, t of 1 equals 1. Okay, this one is definitely really an interesting problem. Let's go ahead and tackle this one on, see how we can solve this. So we get t of n equals t root of n, and n plus 1, because the data of 1, I'll just pick 1, because that's good enough. So this is really not so simple to find this pattern. So what we can do right now is the following. We can do a substitution. So we're going to say let n equal 2 to the power m, and therefore m would have to be log 2 of n. So we're going to rename n. We're going to rename it to a new value. So we're going to set n equal 2 to the power m, whatever that is. So we're going to substitute, we're going to say t of 2 to the power m equals t 2 to the power m over 2 plus 1. So we just substitute 2 to the m in there. And now we're going to rename this recurrence. So we're going to rename t of 2 to the power m. We're going to rename. We're going to set basically t to the power n. We set that equal to t to the power 2 of m. And we're going to rename this to s of m. So we're just going to basically take t to the power 2 up to the m, and we're going to rename this to s of m. We're going to do that substitution. We're going to rename this and substitute this recurrence to give us s of m equals s m over 2 plus 1. So we just replace these two function calls. So we replace, these two with these two. We just replace those, that's all. So same recurrence, but modified a little bit. We renamed them a little bit. So at this point now, if you want to solve s of m, well, I'm not going to do the whole recurrence or do the whole, how should we call it? I'm not going to do the entire expansion here. We can just already remember this is going to be just log of m. So s of m equals theta log of m. So we know from before, t of n, right here, equals t of 2 up to the power m equals s of m. So that means that t of n equals also theta log of m. And we have to substitute m, because m actually equals log 2 of n. So that means this will be theta log n. So the log of n. So this recurrence relation does actually grow at a slower rate than log of n. Now, you may wonder, well, isn't like root of n has a bigger growth rate than log of n? And the answer is yes. But this recurrence relation, I'm going to sort of scroll up for a second, this recurrence relation is not the logarithmic one, because remember, for log recurrence relation, it's going to be t of n equals t of n over 2. But root of n is going to sort of decrease at a faster rate than dividing it by 2. So this recurrence is not square root of n. It's decreasing at a faster rate than log of n. And in fact, it's going to be log of n, which has a slower growth rate than log of n. Alrighty. So of course I'll do one more similar to this one, and then we'll go into more, and then we'll talk about some more nicer sort of nodes. This one's definitely sort of the elephant in the room, is this question right here. But that's the method you want to do. So if on homework you have a question like this, just try to follow this method to solve it. This can be solved on any type of square root, sort of decreasing. Just you have to modify a little bit for different instance. So let's do one more instance similar to this one. So we'll have t of n equals 2t root of n plus theta log n. Oh my goodness, this one is just, the first question, you're wondering just why? Just why? Why am I doing this? Well, I don't know, it's for the thrill. It's for the thrill, I guess. Maybe. Probably not. Let's go ahead and just sort of, work on this one. So similar to how we did the last problem, t of n equals 2t root n, and then plus, I'm going to pick any base of my log. So right now I'm going to choose log 2 of n as my champion. You'll see in a second why, but I could pick any base I want. So for theta log n, just pick any log you want. And I guess this case, log 2 of n is going to be it's going to nicely work out in this example. So once again, we're in a form that's really not so simple to visualize, the pattern, visualize how it's decreasing. So we're going to let n equal 2 to the power m again, and therefore m has to be log 2 of n. So when we work this one out, so we're going to go ahead and we're going to say t of n equals t of 2 to the power m, because we just replaced n with a new term. So we're going to get t of 2 to the power m equals 2 times t up to 2 to the power m over 2, and then plus log 2 of 2 to the power m, which that will just give you n. Oh, sorry, m. I shouldn't have used n and m because they sound similar, but it's okay. I'll write this out. Because log 2 of 2 to the power m is going to just be m, as we know. So now we have this term set up. So we're going to just simply now, we're going to replace these two recurrences with s of m. So now we're going to set t of 2 to the power m equals s of m. We just have to rename this recurrence. So what's going to happen is we're going to have s of m equals 2 times t m over 2 plus m. So we just only simply replaced that recurrence. So we replaced, just like in the last example, we replaced these two with this. Oops. Supposed to be s right there, my mistake. So we replaced these two just like that. That's all we did. So now we have to solve s of m. Now, I could do that whole expansion method, but I'm going to just sort of not do all that. We already know this one is merge sort. So this is going to give us a result of, well, s of m be theta m log m. And basically we know the following is true because we know t of n equals t of 2 to the power m equals s of m. That means we can just say t of n equals theta m log m. And we have to replace, so we know that m is log 2 of n from our earlier assumption. So going back up here, we know that's going to be the case. So we can basically, just erase all of that. So we're going to replace m with log of n. Therefore, t of n equals theta log n log n. So it's log n times log n. So for the homework or maybe an exam question similar to this, you have to just sort of apply this method. So basically all we're doing, so if I scroll back up, we just replace n with 2 to the power m to get this recurrence, then we just replace this whole recurrence with S of n. We rename this recurrence like that. I think this is sort of, I think it's substitution method. I believe it's what it's called. Or renaming, so substituting variables. So I'm going to say substitution, I'm going to say for right now. That's what I think it's called. Or substituting variables, renaming variables method. One of those two is the right term, I think. And then we get into a position where now it's very simple to work this out. Once we work this out, we just simply replace m's with n's, and that's it. So even though it seems kind of complicated, really it's a very nice mechanical way to work these problems out. So just remember this this procedure on these. So it's not too bad, but it's definitely a very bizarre one, I would imagine, compared to the other ones. And you get very weird answers. Log n times log n. Like, that's got to be some crazy PhD thesis type, algorithm, which I mean, I guess my thesis was not exactly this type of stuff. It was something different, but I guess algorithm based, I suppose. But this is must be a very complicated algorithm that has a runtime of log n times log n. So anyway, so I guess I have a little bit of time. So now I'm going to introduce our final method. So this is sort of the CS477 equivalent of when you do derivatives in calculus. So you learn all those formulas like that, f of n minus f of n minus delta n over delta n, that whole method of doing derivatives, which you learned from calculus. And then it turned out the entire time there was a simpler method to work out, especially for these polynomial functions. It's very simple to do derivatives. You take the exponent, you bring it down, subtract one to the exponent, and you're done. Easy as that. Well, this will be kind of the CS477 equivalent of that, which is known as the Master Theorem. This is sort of like a plug-and-play type method of working out recurrences. Now, it doesn't work for every recurrence, but for most recurrences, this actually works. So it makes solving recurrences a lot easier than what I was spending last week, Thursday, and most of today's class talking about. So suppose you have the following recurrence, t of n equals a times t n over b plus some function, f of n. And of course, as always, t of 1 equals 1. I'll put this there. It doesn't really matter, but I'll put that there. So we have our base case as always. So now we have to have the following constants we have to grab. So we have to look at a, you have to look at b, and also you want to see what's the growth rate of f of n. So those are three important parts. So we're going to compute a value. We're going to say c is going to be log b of a. Log base b of a will be our third constant c we're going to use. So once you have all these ingredients, we have a, b, we know f of n's growth rate, we have this c constant. Now we can sort of, put this all together. So I'm going to go ahead and actually just write this. I'm going to zoom out once I'm done so you can see the entire thing. But there's three cases. So cases of the Master Theorem. So case 1. So if f of n equals O of n to the power c minus epsilon, where epsilon will be some very small constant, but bigger than 0. It'll be probably less than 1. It's a very small constant, but some small constant that's larger than 0. If this is correct, then that means t of n is equal to theta n to the power c. So you have to sort of, you have to look at our recurrence relation. We have to group it to one of three cases. Now, some recurrences don't even work because they're not really set up in a way will even work at all. And I'll show one example where it's not going to work in one case because it's going to fall between two different cases. But that's going to be probably, I'll discuss that most likely next time. I won't have time to go over all of these today, but let's go ahead and just continue with this. So case 2, which is the simplest one to look at. So f of n equals theta of n to the power c. If that's correct, well, then, put also a then over here as well. So then the result will be this. So then t of n, put this on the next line actually. T of n equals theta n to the power c log of n. I think I'll box these in actually. So it's going to be the results. That's the result. And in case 3, and I'll zoom out so you can see the whole notes once I'm done writing this. So case 3 is kind of the weird one, but anyway, f of n equals omega n to the power c plus epsilon. Epsilon is some small constant larger than 0. It's going to be less than 1, or it could be 1 even, but typically pick some constant very small, but it must be larger than 0. So it could be 0.0001, any constant you can think of. And if it works, and also this part here, I don't think this really comes up really ever, but I'll just sort of write this out. This is from the book. So and a of f of n over b is less than equal to z multiplied by f of n, where z is less than 1, and you have a large n value. But I don't think this case really becomes too much an issue, but there could be some scenarios where this happens. But typically, let's focus on the f of n equals omega n to the power c plus epsilon. This part there, I think it's like a complete formality, I believe. But anyway, we'll also, we'll test all this out when we do examples of the Master Theorem. So if that's the case, then t of n equals theta f of n. And I'll box this here in blue. That's the result of this. Let me just zoom out so we can see all of this in front of us. So maybe you can take the whole notes down right there. So that's our Master Theorem. So we take a recurrence that kind of follows that pattern, which I showed above. I don't want to scroll up right now, but we have this recurrence. Don't write this note down. I'm just going to put this here just for reference. So if we have our recurrence in this type of form, then for most of the time, you actually can group this to one of 3 cases, and then you have your problem solved. You don't have to do any crazy tree method, or you don't have to do, let's see, what was I going to say? You don't have to do any expansion method. You just use this Master Theorem to solve it. So this is the equivalent of that shortcut for derivatives in calculus. So we have all that stuff we went over, but it was still good to understand how these recurrences are solved. And of course, for the homework and for the exam, so for the homework assignment, I'm going to have you use Master Theorem, but also just because I'm a really bad and terrible instructor, you're going to have to actually work out the problem using the expansion method or use the tree method. And additionally, you have to also show Master Theorem as well. And the good part about that is, at least if you know the answer to the recurrence, then when you're working out the recurrence using the expansion method or a tree method, you kind of know what the answer already is. So it definitely makes it easier to figure out. You have to just sort of, I guess, reverse engineer a solution, I suppose, is the right word. So now some of the problems on the homework, you really can't use the Master Theorem on. So for example, that antiderivative method, you can't apply Master Theorem on that one. And the square root method, or that substitution method, you can apply it, but not on the whole problem. Let me just scroll up for a second here. So right here, when you have S of m, so right in this situation, you can apply Master Theorem right here. That is actually in the form of Master Theorem. So you can apply that Master Theorem on that part. So you have to kind of get the problem into a form where you can use Master Theorem. So right there you can, but you can't use it. You can't do it right on this formula, but you can do it if you break it down far enough. Then you can actually use Master Theorem. So that's basically the Master Theorem's definition. Let's go ahead and maybe I'll do one example or two since I do have a little bit of time left. Just, maybe I'll do like one. I'll do one example for right now. Just one example will be good enough. So let's go ahead. I got my notes here. So I suppose, for the exam, you wouldn't have memorized the Master Theorem. And in fact, even if I had an exam in paper form, like the regular way classes are done, I would probably give you Master Theorem actually on the exam, like the formulas. You have to figure out, the result, but memorizing it though is kind of, why do that? I mean, it's silly to memorize stuff because you can look anything up. So it's more important to understand how it works than memorizing a formula. So here's a very simple example of the Master Theorem, but I'm going to go ahead and cover examples from before, just to kind of see that I didn't make a mistake with my expansions and my tree method and so forth. So in this example, well, A is going to be 1, and B is going to be 2, and F of n is going to be just simply 1 in this case. And then C is going to be log B of A is log 2 of 1, which I believe would be 0, because anything log of 1 will always be 0. So log E of 1, log anything of 1 will be always 0. Okay, so let me go ahead and look at the cases notes here because I can't memorize the Master Theorem to save my life. So let's look. So basically, the simplest way to do these is look at case 2 first. Just like in Rick and Morty, we have Vindicators 2. We start with Vindicators 2, which actually is Vindicators 3, but we start from Vindicators 2. So I guess the best idea is start from case 2. That's the simplest case to eliminate or match with. So case 2, let's see. So f of n does equal theta of n to the power c. Well, n to the power c is n to the power 0 or 1. F of n does equal theta of 1 or constant, so case 2 applies. So there we go. So this is going to be case 2 is going to match. This problem matches with case 2 of Master Theorem. So then we can just go ahead and solve this. So then it's going to be theta of n to the power 0, or just 1, multiplied by log of n. And I believe that is correct, actually. That is this one is binary search. I believe this recurrence. So theta log n is actually the correct result with this. So far, so good. I'll just do one more example, and then we'll call it a day. Just do one more. That was too simple of an example, I think, to end class with. Cool one. So number 13. So 13th recurrence in our set of recurrences. So we'll have t of n equals 9t n over 3 plus theta n. And I guess I'll just put t of 1 equals 1 just to be consistent. Okay, so in this case, a is going to be 9, b is going to be 3, and f of n is going to be just n, or n to the power 1. I'll put that 1 there just to help us, with this problem. And then c is log base 3 of 9, which I believe would be 2. Yes, that is 2, just to check my work. So going back to the Master Theorem, as always, just like with the Vindicators, start with Vindicators 2 first, which is going to be actually Vindicators 2 in this case, not Vindicators 3. So let's start from the second case. So, okay, so c is going to be 2. So is f of n equal to theta of n to the power c, or n to the power 2. And it's not the case, actually, because f of n is linear, and theta n squared is quadratic, so f of n is not theta n squared. So case 2 is eliminated. So we have either case 1 or case 3 remaining. Let's see case 1 for a second. So for case 1, we have n equals big O of n to the power c minus epsilon. So c is going to be 2 in this case. So epsilon, as long as epsilon is less than 1, so epsilon could be 0.5, 0.1, all of those, it will actually work. As long as epsilon is not bigger than 1, but we have to pick just one epsilon, just pick one constant. So I'll pick 0.1. If that's the case, this actually holds. Therefore, case 1 is what's going to happen. And there's no way the cases can overlap with each other, so only one of these three is going to be correct. So for case 1, basically, the result's going to be theta, and it's the n to the power of c, where c is 2, so theta n squared is the result of this problem. Because the result would be just theta of n to the power of c, and we know c is 2, so n to the power 2, n squared. And that's that. So I'll do more examples of Master Theorem next time. We'll go into actually now learning about actual divide and conquer algorithms afterwards, after we finish the Master Theorem content. Other than that, I guess, take care, you guys. Stay safe. Thanks for watching, and I'll see you on Thursday.